6.2, perpendicular and angle bisectors. Now, first of all, a perpendicular bisector, if we take a look at the picture here before I show you what the definition is, perpendicular means 90-degree angle. Okay, bisector means to bisect or cut in half. So if we take a look at this segment AB, okay, we have another line that is perpendicular to it, meaning hitting it at a 90-degree angle. And then these two little tick marks means it's being cut in half. So then the statement down here says that CP, the vertical line, is a perpendicular bisector of AB. So our official definition, a perpendicular bisector is a line, a ray, or a line segment that bisects an angle or line segment at a right angle. And then specifically for bisect, I'm going to add on here cut in half. Okay, now our perpendicular bisector theorem, there's an actual theorem that goes along with this, says this: if a point is on the perpendicular bisector of a line segment, then it is equidistant from the endpoints of the line segment. Now in here we have this word equidistant, and equidistant means equal distance. So let's look at what's going on here. So if a point is on the perpendicular bisector, so we still have AB and we still have P, which is and then we have CP, which is our perpendicular bisector. We have this point C, which is on the perpendicular bisector. Then I know that this point C is the same distance to A as it is to B. So by the perpendicular bisector theorem, we can say that AC is congruent to CB. They are the same length. Now, the converse of the perpendicular bisector theorem, and converse kind of means in my head, this is not the actual definition, but like the opposite. Okay, so if it's a perpendicular bisector, we know this. But converse means going the other way. So if we know this, then we know it's a perpendicular bisector. So what the converse says is that if a point is equidistant from the endpoints of a line segment, then it is on the perpendicular bisector of the segment. So this time, do you notice they're already telling us that AD is congruent to DB because we've got those two little tick marks. So because we know that, then from that we know that point D is on the perpendicular bisector, or it will be on the perpendicular bisector when you extend it through. Now, before I let you use the perpendicular bisector theorem, we're going to prove the perpendicular bisector theorem. In order to do this, we're going to do a two-column proof. Okay, so before we actually go through it, I'm going to set it up. So we're going to do 2 columns. We're going to put work. We're going to put reasons. We're going to put number 1, which is going to be our given. Okay, now CP, which is a line. Okay, so we're going to do 2 arrows there, is the, and I'm going to abbreviate, perpendicular bisector of AB. And notice on AB we don't have the arrows because AB over in our diagram here is a segment. Okay, CP is a line. Now we are trying to prove the perpendicular bisector, which says, okay, if this is a perpendicular bisector, then AC, or in this case, the way they're saying it, CA is going to be congruent to CB. So let's see what we're going to do here. I'm looking at my diagram. I know that CP is the perpendicular bisector of AB. Do you guys notice these 2 triangles? Kind of forms 2 triangles. Okay, well, I'm looking at those 2 triangles and it looks like I have a hypotenuse here and I have a hypotenuse here, and ultimately I'm trying to prove that the 2 hypotenuses, or however you say that, are congruent. Well, what if I could prove that the two triangles are congruent? Doesn't congruent mean same size, same shape? So if we have two triangles that are congruent, then all of the parts are the same. So what I'm going to start with here is I'm going to start with AP, and I'm going to start with BP. And I'm going to say AP is congruent to BP. Now, the reason I know that, okay, is because this is a perpendicular bisector, which was given. Okay, and it specifically says bisect. And if I'm going to bisect something, that means I'm going to cut it in half. Well, if I cut it in half, that means the two sides are the same. So that is the definition of bisect, which essentially was part of our given, because it was given to us that it's a bisector. Okay, now number 3. I know this part is equal to this part. Well, what about these angles? Do you see this angle in here? What do we know about this angle? This angle's 90, so I know this angle's 90. So then I'm going to say, okay, well then angle APC is congruent to angle BPC. Well, I know that because they're both 90 degrees, which again was part of the given. And even more specific, we could say definition of perpendicular. If it's perpendicular, then it's going to intersect at a 90-degree angle. So right now I have a side and I have an angle that's congruent to one another. So if we remember anything from last year, that's a side and an angle. What if I could get another side? Well, what do I know about CP? Well, step 4, I know that CP is congruent to CP because it's the same line. So whether it's on this triangle or this triangle, it's the same thing. So that is going to be our reflexive property, because it's like looking at yourself in a mirror. It's reflecting. So now I have a side, I have an angle, and I have a side of both triangles. So I know those triangles are congruent. So step 5, I'm going to say that triangle, and use a little triangle symbol, APC is congruent to triangle. Okay, and make sure you're matching here. If you started out here A and went into P and up to C, you have to start out at B, into P, up to C. So triangle BPC. And the reason I know this is because of the side, angle, side theorem. Now, if the triangles are the same, then I know all of their parts are the same. So then I know, okay, well, if this triangle is the same size as this triangle, then I know this side is the same length as this side. So now I can say that CA is congruent to CB. And the reason I know this is because of corresponding parts of congruent triangles are congruent. Some teachers call that CPOC-TOC. Some teachers don't use all that. But what this means, corresponding parts of congruent triangles are congruent.